Okay, me again. Any questions? Any questions about anything? Before we move on? Okay. Just remember, I have to get chalk out because the room is low. All right. So last time, introduced the discrete-time Fourier transform. So dTft. And we say that at signal x of n, discrete-time signal x of n, and a 2 pi periodic function x hat of omega hat are a dTft pair when one or both of the following equations holds. One of them is this one, x hat of omega hat is equal to the sum from n equals minus infinity to infinity, x of n e to the minus j n omega hat. And the other one is this one, gives you x of n in terms of the dTft. And we have names for these two equations. This one is called the analysis equation. And this one is called the synthesis equation. Okay, and first example of dTFTs we saw before we even mentioned the name dTFT was frequency response and impulse response of a causal FIR system. H of n and h hat of omega hat are a dTFT pair. Last time, after noting that, we moved on, we did some examples, and we talked about, you know, like delta, shifted delta, pulse, P of n, whatever. Came out to be a Dirichlet thing. You know, we did one where you had a pulse in the omega hat domain. It came out to be a sig function in the time domain. And we also talked about some operational rules and properties. And the operational rules we dealt with last time included the time shift rule, and we're going to be using these two today. So I just want to remind you that we talked about them, time shift rule and the frequency shift rule. And there's going to be others, well, one other, and the other one we talked about last time was linearity, but that was less difficult. Okay, so anyway, moving right along. What is the dTFT anyway, besides a mathematical thing you can do to a signal? What is it? Well, it turns out that you can think of the dTFT as, in some sense, describing the quote-unquote frequency content of the signal x of n. Now, the weird thing is, you may come up, you know, what could the phrase frequency content mean for an arbitrary signal x of n? Certainly, we understand frequency content for a sinusoid, a pure discrete time sinusoid. We have a stem plot for doing that, you know, and remember that if it has frequency omega 0 hat has a stem there, there's going to be a stem at every single frequency that's a 2 pi shift of omega 0 hat. So frequency content of a discrete time sinusoid or a linear combination of thereof makes perfect sense. Okay, but what is like the frequency content of another kind of signal? You know, a signal that doesn't have any sort of sinusoidalness to it. You know, what could that possibly mean? Well, the rationale. What I'm going to do first off is I'm going to give you sort of a Riemann Sum kind of reason for thinking of this x hat of omega hat as being frequency content description. And then I want to do an example where you have a signal that intuitively has frequency content, and you want to see how its dTFT reflects that. So anyway, first off, here's a sort of an assertion. Assertion is as follows, that x hat of omega hat represents, in some sense, a description of the quote-unquote frequency content, whatever that means, whatever that might mean, of the signal x of n. Okay. Why? Why does it in some sense represent that? And in what way does it do that? In other words, like, that is to say, when, say, x hat of omega 1 hat is quote-unquote large, x of n has quote-unquote significant frequency content, around frequency omega 1 hat. And if x hat of omega hat 1 is small, then x of n has low amount or insignificant amount of frequency content around omega 1 hat. That's what I mean by represents the frequency content of x of n. Okay. Now, why might this be the case? Well, if you look at the synthesis equation, so look at the synthesis equation. What does it do? In some sense, what it does is it represents the signal x of n as a continuum superposition of pure sinusoids, okay, whose coefficients, the coefficients in that continuum superposition are the values of x hat of omega hat. So in some sense what this does is it exhibits x of n as what one might call a quote-unquote continuum superposition. Physicists love the word superposition for, like, I've probably said this before. Back row Sam knows this, I know because he's taken AP classes, but superposition is one of the physicists' favorite words, okay? And all it means is linear combination, period. That's all it means. All right, so exhibits x of n is a continuum superposition of pure sinusoids. And to be fair, they are pure complex exponential sinusoids. And the coefficients, the quote-unquote coefficients in the continuum superposition are the values of x hat of omega hat times 1 over 2 pi, but who cares? Okay? So you're taking all the different possible frequencies, all the different possible values of omega hat between minus pi and pi, and that covers all of them really because they're the same frequency, 2 pi periodic in discrete time. Taking all the different possible frequencies, all the different possible sinusoids of those frequencies, all the g and omega hats as omega runs over all the possible omega hat values, and superposing them, adding them all together using x hat of omega hat as the quote-unquote coefficients in the continuum superposition. Integrals are continuum superpositions, and when you first learned about integrals back in high school calculus or Math 1910, you probably first saw them expressed as Riemann sums, okay? And the book does this, and so I think for completeness purposes I should pay some attention to it, so you can make this a little more explicit. By approximating the synthesis equation approximating the integral in the synthesis equation by a Riemann sum. Okay, so remember what a Riemann sum is. You want to do an integral. You divide the interval of integration up into little pieces, and you do a staircase approximation to the function you're trying to integrate, and you add up the areas of all the little stairs. So what does that come out to be for this? Okay, so specifically I'm going to let cap L be large, and I'm going to let omega hat sub k equal minus pi plus 2 pi over cap L times k. And this is for 0 less than or equal to k less than L. And then the Riemann approximation to this integral gives you x of n is approximately equal to the sum from k equals 0 to L minus 1 of 1 over 2 pi x hat of omega k time, that's the height of the stair, whose left side is at omega k, times the width of the stair, which is just k 2 pi, or is just 2 pi over L. And the 2 pi's cancel, you can pull the L out, so that's equal to 1 over L sum from k equals 0 to L minus. I forgot one term there. It's e to the j n omega hat k times the width of the stair. So it's going to be 2 pi over L. And so that in turn equals 1 over L sum k equals 0 to L minus 1 x hat of omega k hat times e to the j n omega k hat. Now, this might remind you of a homework problem. You had a homework problem associated with one of the labs where I talked to you, or the problem talked to you, I should say, about how MATLAB computes integrals using sums and whatever. So this is kind of like a homework problem that you've seen. But what does this show you? This shows you that x of n, right, is approximately equal to the sum of a bunch of pure sinusoids. Right? Each term in this sum is a pure sinusoidal, if you think of it as a whole signal, is a pure complex exponential sinusoid, e to the j n omega hat k, with a number in front of it, namely 1 over L times x hat omega hat k. So this shows that, first of all, x of n is approximately equal to a linear combo of pure sinusoids, sinusoidal signals. And what are those pure sinusoidal signals? They're e to the j n omega hat k, as k runs from 0 through L minus 1. And the coefficients in this linear combo are just going to be 1 over L times x hat of omega k hat. So the value of x, the value of x hat at one of these frequencies, omega hat k, that are approaching a continuum, gives you the amplitude of the term in this approximation of x of n as a finite linear combo of pure sinusoids. Okay, so in this sense, x hat of omega hat k represents the amplitude of the frequency content of x at frequency omega hat k, and in the limit, that's what's going on. Right? So that's a kind of a math justification for, okay, Kinjal. Okay, I guess what I meant by continuum superposition is a linear combo of an uncountable infinity of things. What is the uncountable infinity of things here? The uncountable infinity of things is the uncountable infinity of signals e to the j and omega hat as omega hat runs from minus pi to pi. Every single value of omega hat gives me a discrete time signal, e to the j and omega hat. And there's a continuum of such omega hat values, so that's what I meant by a continuum superposition. That coefficients, an integral is always like a continuum superposition. That's, I don't know. I can't read any more clear than that, at least today. Maybe if I think about it, maybe next time I'll come up with something better. All right. So far, so good? Okay. So, I promised you that after doing this math kind of reasoning, so this gives us sort of a quote-unquote math justification for the kind of mantra, quote-unquote, x hat of omega hat exhibits frequency content of x of n, quote-unquote, mantra. Okay? Let's do an example that builds, in my opinion, better intuition for this mantra. So let's look now at an example of a signal x of n that we intuitively think this x of n should have frequency content around frequency omega 0 hat. So intuitively has high frequency content. Let me put this all in quotes. I shouldn't say high frequency, because high frequency sounds like high frequency, you know. So has significant, how about that? Frequency content at frequency at or around some specific frequency omega hat 0. Okay? And has a DTFT that exhibits this fact, that shows, that has significant sort of mass around omega 0. So that illustrates, that corroborates the intuition. Okay? What is the signal going to be? Our signal is going to be x of n equals e to the jn omega 0 hat when n is between, say, minus L and let's use cap n. N is between minus n and 0 otherwise. Okay, so this x of n is a truncated discrete time pure sinusoid. So i.e. x of n is a truncated pure sinusoid of frequency omega 0 hat. Now, we think of this x of n as having significant frequency content at frequency omega 0 hat for obvious reasons. And the bigger you make n, the more it looks like a pure sinusoid of frequency omega 0 hat. Okay, so anyway, we think of this x of n intuitively has frequency content around frequency omega 0 hat. Let's figure out its DTFT and see whether the DTFT corroborates that intuition. How do we find the DTFT? Well, I told you we were going to use the time shift rule and the frequency shift rule today, and this is where they come in. All right, so let's find x hat of omega hat And we're going to use, en route to this, the time and frequency shift rules. Okay, so how do we do this? Okay, plus an example from last time. What was the example from last time? It was that pulse of length capital L. So first let Q of n equal 1 when minus cap n is less than or equal to n less than or equal to cap n, and 0 otherwise. Okay? Then x of n is what? Then x of n is equal to e to the j n omega 0 hat times q of n. Right? See the definition of x of n? If you just take e to the j n omega 0 hat and multiply it times this flat 1 that goes 1 from minus n to n, you get x of n. By the frequency shift rule from last time, and I'm not going to write the rule down again, x hat of omega hat is just going to be q hat of omega hat minus omega 0 hat, where q hat of omega hat is the dtft of q of n. All right, so that's where we use the frequency shift rule. X hat of omega hat is this. Now we've got to find q hat. What do we do to find q hat? So now we need q hat of omega hat. This is where the time shift rule comes in. Recall from last time, we had this example. If you take the signal p of n, which is 1 from n running from 0 to, say, cap L, minus 1, so we did it this way, did it the Python way, and 0 otherwise. That had dtft p hat of omega hat equals Dirichlet thing times e to the minus j L minus 1 over 2 omega hat. Okay, that was one of our examples from last time, right? Well, you can look it up, or you can pull up the other lecture on your screen and you'll see it's one of the examples. Okay, so what about this p of n versus this q of n? The q of n goes from minus n to n, the p of n goes from 0 to L. If I pick a good value of L, I can just make q a shifted version of p. How about that? So if we pick L equals, what does it have to be? I think it's 2n plus 1. If you set L equal 2n plus 1, what does that mean? That means that n is equal to L minus 1 over 2, right? Then q of n is just going to be p of n plus cap n. And you may have to think about that for a second, but it turns out to be the case. If you pick L equals 2n plus 1 and you shift that p of n to the left, you get this q of n. Okay? And by the time shift rule, the dtft of q of n so from the time shift rule, it follows that q of n, because q of n is equal to p of hat n plus n, q hat of omega hat is e to the minus j minus n omega hat times p hat of omega hat. And the minus signs cancel, n is L minus 1 over 2. And look, conveniently, this factor in front, e to the j L minus 1 over 2, cancels e to the minus j L minus 1 over 2, and this just comes out to be Dirichlet thing, dl of omega hat. And remember, the formula for that is sine L omega hat over 2 divided by sine omega hat over 2. So this is the dTFT of Q. It's a Dirichlet thing with no phase even. Well, it goes to minus 1 when the numerator is negative, but who cares? Or it goes to, I should say, pi when the numerator is negative. And x is just a shifted Dirichlet thing, because x hat is just a shifted q hat. So, what does x hat of omega hat look like on minus pi to pi? X hat of omega hat is just going to be q hat of omega hat minus omega 0 hat, which is just Dirichlet thing of omega hat minus omega 0 hat. And characteristically, or colloquially, however you want to say this, x hat of omega hat is a Dirichlet thing centered on frequency omega 0 hat. So this is what it looks like on minus pi to pi. X hat of omega hat versus omega hat. So say, or versus omega hat. So that's minus pi. So say omega 0 hat is here. It's going to be Dirichlet thing, going down like so. And we're not going to worry about what it is outside of pi and minus pi because it just repeats, it's periodic. It goes up again, but who cares? I want you to get the basics of this picture. What's the peak here? Quick. Somebody, what is the peak? What is the peak? Morgan. Yes. It's L. I'm trying to remember, like, Morgan, were you the one who was wearing red shoes at the prelim 1? I was trying to, there was somebody, I was confusing you with somebody else, and I was trying to figure, I'm trying to learn people's names, obviously, in the class, but if you see this video, send me an email or write on Piazza if you were the one who was wearing red sneakers at the prelim. Because I noticed because I was wearing these red sneakers, and I thought, oh, he has nice red, oh, I have red sneakers on too. So anyway. All right. So that's what it looks like. And what are the zero crossings? Remember what the zero crossings were? In the Dirichlet thing, it's when L omega hat over 2 is a multiple pi, so this is going to be omega 0 hat plus 2 pi over L. This is omega 0 hat plus 4 pi over L, etc. And it's symmetric. So this is omega 0 hat minus 2 pi over L here. All right, now what was the goal of this example? The goal of this example was to take a signal that our intuition tells us has significant frequency content at or around frequency omega 0 hat. And this is that signal. It's a truncated omega 0 hat sinusoid. Figure out its DTFT and make sure that the DTFT corroborates that. And sure enough, it does. Look at x hat of omega hat. It's got a big mountain right on omega 0 hat, right? And it dies away from omega 0 hat. So yeah, so the DTFT of x hat of x of n reflects the fact that x has significant frequency content at omega 0 hat. It's not all at omega 0 hat, but most of it's right around there. Now, I commented earlier that as you let cap n go to infinity, and by the way, this L here, this L is 2n plus 1. Right? From the given expression for x of n is in terms of that cap n, and we let L equal 2n plus 1. Okay? Somewhere. Yeah. All right. What happens when we let n get bigger and bigger and bigger? So let n grow. What does that imply? That implies that x of n looks more and more like a quote-unquote pure, complex, exponential, omega 0 hat sinusoid. Okay? It never quite gets there because n is deemed finite. But anyway, it looks more and more like a pure sinusoid. So what do we think? What do we think? That its frequency content should be more and more and more concentrated on omega 0 hat as n gets larger and larger and larger. And if you look at this picture, sure enough, that's exactly what happens, right? As n gets larger, so does L. Height of the central peak gets higher and higher and higher. Meanwhile, the width of the central peak gets narrower and narrower and narrower because these first zero crossings are always going to be at omega 0 hat plus 2 pi over L minus 2 pi over L. And that difference, 2 pi over L, is going to 0 as n goes to infinity. Okay? And meanwhile, the height of the central peak in x hat omega hat goes up, and the zero crossings close in, on omega 0 hat, meaning that quote-unquote x hat omega hat is more and more focused I'll put that highly imprecise word on omega 0 hat as n increases. So that limiting stuff goes along with our intuition. Now, does anybody know off the top of their heads what this, if I let L go to infinity, what does this graph approach? Critic. Yes, it does. It approaches a Dirac delta function. Has everyone ever heard of a Dirac delta function? Yes, no? Where'd you hear about it? Diffie-Q? Diffie-Q for everybody? Circuits maybe? Okay. Dirac delta function. We're not going to do those in this class. The book doesn't. There's ways of doing a lot of the sampling stuff with Dirac delta functions, but to me it's just not as clean, so I don't like to do it that way. The delta of n in discrete time, that's an actual discrete time signal, but the delta of t in continuous time, that's not even a signal. You know, it's got this kind of legendary bunch of properties, like it's infinity at 0, it integrates to 1, even though it's 0 everywhere, but you know, it's just crazy. It's the derivative of a unit step. You know, I don't even want to go there. But as it happens, as you let n go to infinity, this picture approaches a delta. So in some sense, what some people would say, it actually approaches 2 pi delta. 2 pi delta. Some people would say the dtft of a pure exponential sinusoid is 2 pi delta of that frequency. But we don't. Okay, so caution. at least in this class, the signal, the pure sinusoid x of n is equal to e to the j n omega 0 hat for all n has no dtft. In other classes, where Dirac delta functions are allowed, people will say that the signal x of n equals e to the j n omega 0 hat does indeed have a dtft, and that dtft is 2 pi delta of omega hat minus omega 0 hat. Okay, we're not going to do that in this class. We're not using, this is not here. Not here. This does not happen here. And I'll save up Dirac stories for Ece 3250, unless you want to hear one. You don't. Okay, I think they're pretty funny, but Dirac was kind of an oddball. You know, he, like, retrospectively, the people write about him say, well, he was on the spectrum. You know, in other words, he was probably like kind of Asperger-ish or something. I don't even know if that's an accepted word anymore for an autism spectrum disorder. But you know, he had a hard time reading like social cues and whatever. And you know, there were stories. There was this book that someone put out a couple years ago, like five, 6 years ago, called The Strangest Man, and it was a biography of Dirac. So think of it that way. That's the way people thought of him. You know, but there are stories like this guy he was at the University of Florida at Gainesville, Dirac was, toward the end of his career, and somebody came from Europe to visit him, and they went out to lunch or something, and they were just sitting there in total silence, nothing, no conversation or anything, and the guy from Europe was thinking, I've got to think of something to talk about. So he said to Dirac, have you seen any good movies lately? And Dirac looked up from his food and said, why would you want to know? See, he was that kind of guy. Okay, so anyway, it takes a person of that kind to invent something as monstrous as the delta function. Anyway, that's math, sociology 101 for today. Okay, so now I hope you buy in to the moral of the story is x hat of omega hat exhibits frequency content of x of n. All right, and by the way, because you know, in this class, because this pure complex exponential sinusoid does not have a dtft, we represent its frequency content with stem plots. Stem plots are safe. Stem plots don't cause alarm like this does. But in any event, x hat of omega hat exhibits frequency content of x of n, and for this reason, we often refer to x hat of omega hat by analogy with the linear convos of sinusoid stuff that we spent the first several weeks on as the spectrum or spectral representation or frequency domain description any of those commonly used phrases that we've met before in other contexts of x of n. So no one's going to misunderstand you if you say, well, we figured out the spectrum of this signal, and you know, they'll know immediately that you're talking about its dtft. And again, because signal and DTFT determine each other completely, knowing the spectrum isn't just knowing something about exponent, it's knowing all about exponent. All right, so one final operational rule associated with DTFTs. And that is the convolution rule. So one final important DTFT operational rule is the convolution rule. And what does that say? That says that if you have a signal x of n with DTFT x hat of omega hat, and h of n is another signal whose DTFT is h hat of omega hat, and I'm picking h as the letters in question here because we're going to be using them. That h suggests something to you, doesn't it? Then the signal y of n, which is the convo of h and x, that's going to have DTFT y hat of omega hat equals the product, functional product of h hat and x hat. So, convolution in the time domain DTFTs to multiplication in the frequency domain. And essentially every transform that you ever encounter in signals and systems and circuits and whatever has a convolution rule, okay? And those convolution rules all say convolution in the time domain goes to multiplication in the whatever else domain. And in this case, it's the omega hat domain. In continuous time signals, it's the F domain. In Laplace transforms, it's the S domain. You know, it's all this kind of stuff going on, right? So anyway. All right, it's easy to show this. It's easy to prove it. I'm not going to do it in class because, you know, unless you want me to. Okay, how many people want to see like a two-line proof of that fact? How many don't? Okay. How many abstentions? Well, abstentions win as usual. Like not a single person in this room raised his or her hand. But at the same time, everybody in this room, except for me, raised a hand. See, that's logically correct what I just said? Think about it. Okay, so I won't do a proof. It's easy to show, easy to prove. This by using what I would use the analysis equation and time shift rule. But you know, that's one way to do it. I'm not going to prove it. But what does it reveal to us? It reveals, along with this assertion, this moral of the story we told earlier today, it reveals why we like to think of, say, systems with frequency responses, causal LTI systems with frequency responses, or causal FIR systems at least, in fact, any LTI system with a frequency response, as frequency selective filters. Okay, now why? Right, so this along with the sort of the quote-unquote moral thing above gives us a reason, gives us a way of looking at LTI systems as frequency selective filters. Frequency selective, not selective. There's no word selective. Okay, so why? We've already seen, like, when you have a system, you have impulse response h of n is going to be in a DTFT pair with frequency response h hat of omega hat. And comment here, a little comment here, we haven't officially talked about frequency responses for arbitrary LTI systems that aren't necessarily causal FIR systems, but it's the same. So note, haven't discussed frequency response of arbitrary LTI systems, i.e. not necessarily causal and FIR. But it's a thing. Okay, the frequency response of an arbitrary LTI system. Turns out some LTI systems have frequency responses and some don't. The ones that do are the ones that have h hat of omega hat have a DTFT for their impulse response. Okay, so let me, I might as well say it. So what about that? Before we move on. Given an LTI system, with impulse response h of n, we say that the system has a frequency response when h of n has a DTFT. And not every system, not every LTI system does. So we say the system has a frequency response when h of n has a DTFT. And in that case, that DTFT is the system's frequency response. So the system's frequency response is then that DTFT, h hat of omega hat. Okay, so that relationship, the frequency response, impulse response, DTFT pair relationship, that pervades all systems that have frequency responses. It doesn't just apply to causal FIR systems. All right, so given that, we have two things going on. And these are two things that are easy to conflate. And I always caution folks not to conflate them. So let me tell you what I mean. We have one already, and it goes like this. So here's two things related, not the same. Please try not to conflate. I'll just say please don't conflate them. All right, so one thing is, if I take x of n, pure complex exponential sinusoid, and I put it into the system that has impulse response h of n and frequency response h hat of omega hat, what comes out is y of n equals h hat of omega 0 hat e to the j n omega 0 hat. This is, remember we were talking about finding the frequency response by using the picture? This is the picture. E to the j n omega hat goes in, h hat of omega hat e to the j and omega hat comes out. Here I'm just pinning down omega hat to some omega 0 hat. So this is the eigen-input thing, remember? Right? Remember we said that for LTI systems, or at least for causal FIR systems, e to the j and omega 0 hats were like eigeninputs. You put one in, what comes out is a constant times it. Sure enough, that's the case here for any LTI system with a frequency response. That's one picture. So let's call that 1 star. What is the other picture? All right. The other picture is you take any x of n that has a DTFT, x hat of omega hat, and you put that into the system. What comes out is y of n equals h of n convolved with x of n. So y hat of omega hat is the product of h hat of omega hat times x hat of omega hat. This picture, which I'll call double star, is fundamentally different from this one in a couple of ways. The top picture, star, single star picture, is about, so it pertains to how h hat of omega hat determines system response to arbitrary, no, to pure discrete time sinusoids. Okay. Double star pertains to how h hat of omega hat determines system response to DTFT-able inputs, inputs that have DTFTs. Remember, in this class, e to the j and omega 0 hat does not have a DTFT. So, inputs that have DTFTs. Okay. But in either case, this supports our intuition that these are frequency selective filters. Why? Star telling us how the frequency response determines the response to pure sinusoids, that says that if h hat of omega 0 hat is big, then the system amplifies the sinusoidal frequency omega 0 hat. If it's 0, it kills the sinusoidal frequency omega 0 hat. If it's small, it attenuates it. So it filters out some and amplifies others. What about double star? So the sort of the filter worldview, we've supported that already in the context of star is clear in some sense. What about the filter worldview in the context of double star? We think of x hat of omega as the frequency content reflecting the frequency content of x. So as for double star, x hat of omega hat reflects frequency content of x of n. Y hat of omega hat does the same for y of n, reflects the frequency content of y of n. And because y hat of omega hat is h hat of omega hat times x hat of omega hat, you see that you get the frequency content for y. So you get the frequency content in y of n by reshaping, or whatever, the frequency content in X by means of H hat of omega hat. So reshaping / filtering whatever frequency content in X of n by means of, according to the system's frequency response. H hat. All right. Fair enough. And when we talk about ideal filters in a little bit, you'll see kind of an extreme example of how that reshaping can occur. Okay, so are we good so far on this stuff? Any questions? Back row, Alex? We have at least two Alices in the room. There's Alex, who sits like in the second row, and he's also in my other class. Hi, Alex, and back row Alex. So what was your question? Oh. Because, this is because, let me get a piece of chalk. This is because y hat of omega hat is h hat of omega hat times x hat of omega hat. Okay, that's all. That's what I mean by reshapes the frequency content in X into that of Y. Okay, good question. All right. Okay, moving right along, one other sort of general topic in the DTFT realm is this business about autocorrelation, Parseval's theorem, all that stuff. And the book does this, so I think it's worth doing. All right, so here's another sort of DTFT-centered topic. And this is the idea of autocorrelation, etc. All right, so we need a little bit of a background here, a little bit of an assumption that the book isn't that explicit about, but I think it's important. Okay, so anyway, we say a signal. So first off, we say that a signal x of n, we say x of n is, and there's two pieces of terminology here. One of them is classic Ece terminology, okay, and the other one is a more sort of modern mathy terminology that you'll encounter in more mathy contexts. So the classic Ece terminology is an energy type signal How many people have heard that terminology in some other class? Nobody? They don't even talk about it in circuits anymore? Well, I shouldn't say that because I'm so out of the loop on circuits. I mean, I have no clue. You know, do you even still do nodal analysis and things like that, or do you just use SPICE for everything? I don't know. Anyway, we say x of n is an energy type signal or an L2 signal. That's the more math terminology. And you'll hear, if you take machine learning or whatever, you'll encounter that. When the following is true. The sum from n equals minus infinity to infinity of x of n squared exists, so converges. So the sum of the squares of all the values of x from minus infinity to infinity, that's a finite sum. And in this case, this thing here is called the total energy in the signal x. So the total energy in x is the value of this sum. And the reason for this energy terminology is like, you know, classically speaking, X is going to be like a voltage or current, you know, kind of constant, whatever. And energy is going to be like voltage squared or current squared, you know, power, whatever, energy, power, whatever, you know, all those kind of things. And so that's why people think of this. And, you know, a power type signal is one where this diverges, but I don't even want to go there. It's a Jezaro mean kind of thing. But anyway, energy type signal, an L2 signal. Now, it turns out that if X of n is an L2 signal, we can define another function called its autocorrelation. So when X of n is an L2 signal, we can define, and this doesn't necessarily exist when X of n is not an L2 signal, and that's why I'm careful to introduce that assumption. We can define its autocorrelation function as follows. It's going to be a function, and I'm going to call it Cxx of n by means of the following expression. Cxx of n is equal to the sum from m equals minus infinity to infinity of x of m plus n. Okay. So that's the autocorrelation. All right? So far, so good? All right, now notice that Cxx of 0 is what? What is Cxx of 0 when x is real value? How do I get Cxx of 0? I plug in 0 wherever I see n in the expression for Cxx of n. So that gives me the sum from m equals minus infinity to infinity x of m, which is x of m squared, which is magnitude of x of m squared, which is total energy. All right, we're going to come back to that fact that Cxx of 0 is the total energy. You write it bigger so you can see it. Total energy in x of n. All right. So anyway, that's the autocorrelation function. Now, what is the Dtft of the autocorrelation function? The expression we have here for it looks kind of convolution-ish, don't you think? Don't you think? I mean, what's the difference between a convolution would have like x of n minus m here instead of x of m plus n? Okay, but we're thinking that if we can kind of shoehorn this into a convolution box, then we might be able to use a convolution rule for DTFTs to figure out the DTFT of Cxx of n in terms of the DTFT of x. And sure enough, we can. So what is the DTFT? Cxx hat of omega hat of the function Cxx of n. First, what I'm going to do is rewrite the sum. And the way you do this is you set k equal to negative m. I'm just going to do an index of summation change in this sum, and you get Cxx of n is equal to the sum from k equals minus infinity to infinity of x of minus k, x of n minus k. Okay. So far, so good. Now I'm going to let R just be the time reversal of x. So r of n is equal to x of minus n. It's easy to show in this case that the dtft of r, namely r hat of omega hat, is just x hat of minus omega hat. Just plug in to either the analysis or synthesis equation. We have Cxx of n is equal to the sum from k equals minus infinity to infinity of x of minus k. That's just r of minus k times, or r of k, I should say, times x of n minus k. Now we have an actual convolution here. R of k is x of minus k. This is the same as r of n involved with x of n. So the convolution rule tells us that the dtft of the autocorrelation function is the product of the dtfts of x and r. So by the combo rule, Cxx hat of omega hat is r hat of omega hat times x hat of omega hat. R hat of omega hat is just x hat of minus omega hat. But assuming x is real, x hat of minus omega hat, the conjugate symmetry thing, tells us that that's the same as x hat of omega hat conjugate. So this is because conjugate symmetry, when x of n is real, and if you take something conjugate times something, you get magnitude squared of something. So that's what that is. Bottom line, the dtft of the autocorrelation function is the magnitude squared of the dtft of the signal itself. Now, what does this tell us? If we plug this result into the synthesis equation, so if you plug this into synthesis equation for Cxx of n, this is what we get. We get that Cxx of n equals 1 over 2 pi, integral from minus pi to pi, magnitude squared of x hat of omega, e to the j and omega hat, d omega hat. Okay? So far, so good? Now, directly above, we have Cxx of 0 is the total energy in the signal x of n. So if I plug in n equals 0 here, get Cxx of 0 equals 1 over 2 pi, integral from minus pi to pi, x hat of omega hat, magnitude squared d omega hat. And remember, this is the total energy in x of n. And for this reason, because the total energy in x is equal to this integral, people refer to the mag squared of x hat of omega hat as the energy spectrum of the signal x of n. Because by that equation, it shows you how the energy in x of n is sort of doled out over all the different frequencies omega hat between minus pi and pi. Okay, so this equation is y that sounds awful. This equation is y. You can live with it. People call mag squared of x hat omega hat the energy spectrum. Of x sub n. What it does is it shows how, so x hat omega hat squared exhibits the distribution over omega space, omega hat space, of the energy in the signal. And the equality there between Cxx of 0 and that integral, where the total energy in x in that integral has a name. So this equality, the identity sum total energy in x, which is the sum from n equals minus infinity to infinity of x of n squared, equals 1 over 2 pi, the integral from minus pi to pi of mag squared of x hat omega hat the omega hat. The identity, this is known as Parseval's theorem. Or Parseval's identity, or the Plancherel theorem. It has all kinds of, some people say, oh, the continuous time version is Parseval, and if you call that Parseval, you're uncultured. I wouldn't go that far, but some people don't like to call that Parseval. They like to use reserved Parseval for the continuous time thing. Okay. I think that about does my time for today. As I recall, I'm supposed to stop at like 72 minutes instead of 75. Let me just make absolutely sure that I don't want to say anything else today. Well, let's leave it at that. So again, I hope you're doing okay. Honestly, I totally honestly I miss you guys, and just try to make the best of it. And yeah, so there. Okay. See you next time. And now for the awkward moment where I have to turn the video off by going through many clicks. Can't sort of climatically end a class, it's unfortunate. Ready, set,